Welcome back. Today we are going to be looking at lesson 6.4, which is all about factoring polynomials. The process for factoring is what allows us to take a sum and write it as a product. So we are taking a combination of addition and or subtraction and writing it as a product of multiplication. When something is prime, that is a polynomial that cannot be factored. So sometimes we'll come across polynomials that can't be factored at all. And so we call them prime and we can't do any of these methods. So we are going to go through all the methods for factoring here and talk about when they're most useful. And then we'll do some practice with them. So the first method is called greatest common factor, or we sometimes abbreviate it with GCF. And this one, most importantly, is always what we look for first. So we do this method whenever possible. We check for it first in order to see if it can help us simplify a little bit before we maybe try another method. So when we are using the greatest common factor method, we are trying to find a GCF, so a greatest common factor that evenly divides into both terms. So we're looking for the greatest common factor of 9 and 18. So that would be a 9. And we are looking for the greatest common factor of x squared and x. So that would be just a single x. They both have that common factor. So when we take that out, we're basically dividing each term by that. So that would leave me with an x in the first term and a 2 in the second term. When I divide 18x by 9x, the x is reduced to 1, and the 18 divided by 9 is where I get the 2. So that allows us to have a polynomial that's simpler, and sometimes that polynomial in the parentheses there can be factored further using one of these other methods. So the second method that we're going to look at here is factoring by grouping, and we use this method when we have 4 terms in our polynomial. Only works when we have 4 terms. So to do this one, we group the first 2 terms with parentheses and the last 2 terms with parentheses. So we group those together, and then we look for the GCF, like we were just talking about above, for each binomial. So the first parentheses, we're looking for what those have in common, and then we're looking for what the second 2 have in common. So for these first 2, we have x cubed and x squared, so I can factor out an x squared from those first 2. And when I do that, that leaves me with x plus 4. The second set of parentheses, or the second binomial, when we look at 2 and 8, those have a GCF of 2. So I'm going to take that out, and that leaves me with x plus 4. And one thing that's nice about this method is that we know we've done it right if those new binomials in parentheses match each other. So then the last step is to factor out that common binomial. So the common binomial is x plus 4. We're going to factor that out. And then we're going to write what's left over in a second set of parentheses. So we factored that 4-term polynomial by grouping. If we multiply those back together, we'd be right back where we started. Okay, method 3 is the basic method. We use this for trinomials that have a leading coefficient of 1. So trinomials are x squared plus something x plus a constant value. And this works great when we have just that 1 out in front. So we find the factors of c. So factors of this c value. So when I think about -6, that could be 1 times 6, or it could be 2 times 3. And we are trying to find which of those factor pairs can add up to b. So I'm looking for, if I add these together, which ones can make -5. So if we have to multiply by -6, we know that only one of the terms is negative. So if I do 1 plus -6, that's going to give me -5. If I look at the second pair, I can't make only one of them negative and make them add up to 5. If I made them add up to -5, I'd have a -2 and a -3, but then they won't multiply to -6 anymore. So this is my factor pair that multiplies to -6 and adds to -5. So my factors would be x plus 1 for the positive one, and an x minus 6 for the second one. Okay, next method is substitution. So substitution we use for trinomials. Remember that means 3 terms that have degree 4. So they would be in this form, x to the 4th plus something x squared plus a constant. So we call it substitution because we can take this guy and substitute it in and say that u, we use u as just a variable, is x squared. So I'm going to substitute that in for anywhere I can put an x to the 4th, basically. So x to the 4th is x squared squared. So I'm going to write this as u squared, because u is x squared squared is x to the 4th. All right, then I'm going to subtract 3, and again, I'm going to substitute in for x squared, a u. And then the minus 18 we can't do anything with. So now it is a basic, so we're going to factor it the same way. So I'm looking for factors of negative 18 that add up to negative 3. So when I think through that, I can make 3 and 6 make a negative 18 if I make one of them negative, and those added together would equal negative 3. So my factors are u plus 3 and u minus 6. And then we just have to resubstitute back in the x squared here. So we're going to take this and resubstitute it in for the u's. So we're going to say u is actually x squared, and then the plus 3, and x squared minus 6. So now I have factored that. Again, anytime you factor, you can multiply it back together and make sure you get what you started with. Next one is called slip and divide. So we use this for trinomials where it has a leading coefficient out in front. So trinomials, again, are going to be x squared plus something x plus c, or constant. And we're going to do what's called slipping and dividing to figure out how to factor that with an a value out in front. So the first thing you do is you multiply the a value out in front times this constant at the end. So when we do that, we get 20. And that becomes our new c term. So we're basically slipping that 2 over with the c value to make a trinomial that is now I can do the basic method on. Okay, so I'm going to factor this. I'm going to look for my factors of 20 that add up to 9. That's going to be 4 and 5. So multiply 4 and 5, you get 20. Add 4 and 5, you get 9. So my factors here would be x plus 4 and x plus 5. Now, here's where the divide part comes in. We, remember, originally multiplied that 2 into the 10, so now we need to divide it back out. So we're going to divide each of those factors we just found by 2 to move that back. So when we do that, we end up with x plus 2. And then the second one, since 5 is not divisible by 2, we move the 2 out in front and leave the 5 in there, because when I would solve that, I would move the 5 and then I would divide by 2. So it is just rewriting that factor in a different way. They'd still be equivalent. Again, you can multiply those back together and you'd end up back with our original equation of 2x squared plus 9x plus 10. All right, the next method is called difference of squares. So difference, subtracting, and then squares is 2 terms that are perfect squares. So the way this method works, you can kind of see a formula down here for that. This only works again when we have perfect squares. So the first thing we're going to do is we're going to square root the first term and the second term. So those are our squares. So the square root of the first term is 2x, and the square root of the second term is 7. So we use that to fill in this formula over on the left-hand side. So the first factor is a plus b, and the second factor is a minus b. And that is difference of squares. Again, we can double check that, multiply them back together. You'd see that if you FOIL them, the outside and the insides become negative 14x and plus 14x, so those disappear and leave you with just the two terms. Okay, our next method is similar, but it's the difference of cubes. So now we have a difference, subtraction only, doesn't work with addition, of two perfect cubes. So we have a formula again to use once we figure out what the cube root of each term is. So if I cube root each of those, we figure out that a is just x, and b, the cube root, sorry, didn't write the cubes in there, the cube root of 125 is 5. So using the formula over there, that means that my first factor is x minus the 5. And then my second factor is a little more complicated, so it's a squared, which in this case would be x squared, plus the a times the b. So when we do that, a times b in this case would be 5x. And then you're adding the b squared, which in this case would be 25. So that is my difference of cubes. Next one is sum of cubes. So this one is what works when we're adding two perfect cubes together. So we're going to start the same way. Cube root both terms, and we get that a is x, and b, forgot the cubes again. The cube root of 27 is 3. So then again, I'm going to use this formula over here and plug things in where they go. So my first factor is going to be x plus 3. So you can see that's a difference from up above with the difference of cubes. And then my second factor is a squared. So that would be x squared here, minus a times b. That would be 3x. And then plus b squared, which in this case would be 9. So that is my sum of cubes formula that allows me to factor two perfect cubes that are being added together. All right, and then our final method for perfect square trinomials. So perfect square trinomials are 3 terms, that's the trinomials part, and they're coming from still perfect squares, and it can work when they are adding or subtracting, so you can see that difference in the terms. So first thing you're going to do is you're going to square root the first term only. So when we do that, we figure out that a is the square root of that, which in this case would be 3x. And then you're going to square root the last term, which in this case is just a 1. So that means b is 1. And then you're just going to double check that the middle term is 2 times the product of a that you just found and b. And when I do that, I get 6x, which is the product of a and b. So that tells me that it is a perfect square trinomial, and I can use the formula. So in this one, it's 9x squared minus 6x. So we are going to use this down here, and we can factor that perfect square trinomial into 3x minus 1 squared. And again, you could FOIL that back out, and you would get the polynomial we started with. So those are all the methods we might use and the situations where we would use them. So now we're going to practice a little bit with that. For these 8 problems that we are going to do here, we are going to look at the polynomial, decide which method makes the most sense or methods, and then go ahead and factor them. So when I look at this first one, the first thing I always check for, remember, is a greatest common factor. So we always want to make sure that we keep this one as our first check, and then if we need it, use it, and then factor more, or if we don't need it, we don't need it. So this one, 9 and 121, those are not divisible by any of the same factors. So there's no GCF in this one, but I do know that 9 and 121 are perfect squares. So since I'm subtracting, I know that this is a difference of squares. 2 perfect squares that are being subtracted. So remember, when we do this, we square root both terms, and we figure out that a is 3x and b is 11. So then I use that formula which is a plus b times a minus b. And again, I can check my work, FOIL them back together. It would give me 9x squared minus 121. All right, looking at number 2. So number 2, if I'm looking, 2 and 64 definitely have a common factor, and so do x cubed and x squared. So I am going to take out the greatest common factor of these two. So their greatest common factor that they are both divisible by is 2 and x squared. So when I divide that out, I'm left with an x and a plus 32. And then I just double check the polynomial that I'm left with is x plus 32, which is first degree. We can't factor those any further. So that is the only method I need for that one. Okay. Problem number 3 here. So in problem number 3, no GCF, because one is a variable, one is a number. So they're not going to have anything in common there. But I noticed that it's x cubed and 216, and I remember that those are definitely perfect cubes that are being subtracted. So this one is going to be a difference of cubes. So difference of cubes, I'm going to cube root both of them. And that tells me that A is x and B is the cube root of 216, which is 6. So using the formula for difference of cubes, I have A minus B, and then I'm multiplying that by x squared, or A squared, plus the product of the two cubes, and then times B squared, which in this case is 36. And then I just double check the quadratic that I'm left with and just make sure I can't factor that, which I can't in this case. There's no factors of 36 that add up to 6. So we are done there. Looking at problem number 4. So this one, x squared and 36 do not have a GCF. I see that they're being added. They are both perfect squares, but I can only factor things that are difference, not sums of perfect squares. So this one is actually not factorable, which means it's prime. None of those methods are going to work. Okay, number 5. So in number 5, I have a trinomial. It has a leading coefficient bigger than 1. So I'm going to slip and divide here so that I can move that leading coefficient out of the way and make it more manageable. So remember, we multiply those together and we get x squared minus 17x plus 30 as my new c value. So then remember that I'm looking for factors of 30 that are going to add up to 17. So when I do that, let's see, 15 and 2 both need to be negative to add up to negative 17 and multiply to 30. So my two factors are x minus 15 and x minus 2. And then remember, we need to redivide out that number we started with. So I'm going to redivide those by 5. So for this first one, that results in x minus 3. In the second one, 2 is not divisible by 5, so we just slide that 5 out in front. And that is my second factor. Okay, for number 6, in this one, I notice that I have 4 terms. So with 4 terms, I'm going to factor by grouping. So group the first 2, group the second 2 terms. And again, I'm factoring out their greatest common factor. So from the first set of parentheses, that would be an x squared. And when I divide that out, I would be left with x plus 2. And then in this second one, I notice they both have a negative and they're both divisible by 25. So I'm going to factor that out. That's going to leave me with an x plus 2. And again, I kind of know I did it right because I've got the same common factor. So we're going to pull that out in front. factor out that common factor, common binomial, and that's going to leave me with an x squared minus 25. Now, I factored by grouping, but I noticed that I still have a quadratic in this second one, and that quadratic is actually factorable again because it's a difference of squares. So I am going to do a difference of squares now on that second polynomial there, or second binomial. So the first one stays the same. And then I'm going to factor that difference of squares to x plus 5 and x minus 5, because those are the square roots of those perfect squares. And that leaves me with a finished product. Okay, last two problems here. So for number 7, 40 a cubed and 135b to the 6th. I do know that 40 and 135 are both multiples of 5. So the first thing I'm going to do is I'm going to take out a GCF, and I'm going to see if what's left is factorable. So both of these are divisible by a 5. So when I divide that out, I'm left with 8a cubed, and I'm left with 27b to the 6th. So now that I've done that, I notice that 8a cubed and 27b to the 6th, those are both perfect cubes. And so since they're being added, I'm going to do the sum of 2 cubes. So the sum of 2 cubes, remember, we're going to cube root both of these terms that are in there, and the 5 is just coming along for the ride. So my a cube root of 8 is 2, and the cube root of a cubed is just a. My b, the cube root of 27 is 3. The cube root of b to the 6th is b squared. So my sum of 2 cubes formula says that I take those two terms and I add them together. And then my second factor is a squared, so that would be 4a squared, minus the product of those two. So 2 times 3 would be 6. Then I have an a and a b squared. And then b squared, which would be 9b to the 4th. Ooh, I ran out of room a little bit there. Let me write the final answer for you. So we have 5 times 2a plus 3b squared times 4a squared minus 6ab plus 9b to the 4th power. So there is my final factored form. Number 8, our final practice problem here. So when I look at this one, I see that it is a trinomial with a leading coefficient of 1, but it's an x to the 4th. So I'm going to do substitution. So in substitution, I'm using that because x to the 4th, we're going to replace. So I'm going to say that u is x squared. So that means that this is u squared plus u minus 20. So I'm replacing the u with an x squared, or replacing each x squared with a u. So then now it's just a basic. Now it's just a basic problem. So that means I'm just looking for the factors of negative 20 that add up to 1. So in this case, it would be u plus 5 times u minus 4. Those multiplied to negative 20 add up to positive 1. And then I'm going to resubstitute the x squared back in. So that's going to leave me with x squared plus 5 and x squared minus 4. And when I look at that second factor, x squared minus 4, I notice that that is a difference of squares. So I am now going to factor that one. a little bit further. So x squared plus 5 cannot be factored any further, so we're going to leave that alone. And then we're going to factor the x squared minus 4, and that factors as a difference of squares to x plus 2 and x minus 2. So that is our factoring of polynomial with all the different methods we could use. We'll see you next time.